producing 3 watts output power. The transmitter is connected to an antenna having a characteristic impedance of 75 ohms. The connection is made using a lossless coaxial cable with 50 ohms characteristic impedance. Calculate the power delivered to the antenna if the source impedance is 45 ohms and the cable length is 11 lambda. If you can get the picture, it's fine. But if you cannot get the picture, then you can roughly sketch VG transmitter. And then this is given 45 ohms. The characteristics impedance is 50 ohms. And then, okay, this is the antenna. And then you have, what else? The length is given. The characteristics impedance of the antenna is 75 ohms. That means the transmission line is feeding the antenna. You can look at this antenna as your load, which is 75 ohms. So that's power coming in. Available power, P in is 3 watts. The transmitter is capable of producing 3 watts output power. So this P in is 3 watts. And this is a lossless line. In most of these examples, it's going to be lossless transmission line. If it's a lossy transmission line, the calculation will become more complicated. For simplicity, we just leave it as lossless. Capable of producing 3 watt output power means the source and load impedances are matched to the line. That means reflection at the source is 0 and the reflection at the load is also 0. Capable of producing, that means without any reflection, that's what is capable of producing. In actual fact, they are not 0 because the source impedance is not matched to the line impedance. And here again, the line impedance is not matched to the load impedance. It's not equal to 0. Also not equal to 0. You cannot use, so you cannot simply use this formula to solve it. Okay. Under all matched condition, when the reflection at the load and the source is 0, then only you can use this. For under match condition, the characteristics impedance is equals to the source impedance. Sometimes I use source, sometimes I use ZG. Here they're using ZG. So let me change everything to ZG. Also, the source impedance, I also use VG. Under matched conditions, the characteristics impedance is equals to the generator or source impedance, and that also will be equals to the load impedance. If all of them are equal, then the reflection coefficient, gammas of G and gammas of L will be 0. In that case, you can use this formula. So since they are not matched, the transmission line will have reflection at the source. Gammas of S is ZG minus Z0 divided by ZG plus Z0. ZG is 45. The characteristic impedance of the line is 50. So there's a small reflection coefficient. Similarly, you can calculate this reflection coefficient at the load, which is ZL minus Z0 divided by ZL plus Z0. Is equals to 1/5 and 0.2. The reflection at the load is a little bit bigger than the reflection at the source. The reason is because the difference, so the difference is small here. So you get a smaller reflection coefficient. The difference is bigger. So you get a bigger reflection coefficient. There's one more thing that you need to calculate is e to the minus j2 beta L. 2 beta is 2 pi over lambda. Multiplied by the length is 11 lambda. Okay. If we cancel this lambda with this lambda, and then you will have 2 times 2 pi is 4 pi. 4 pi times 11 is 44 pi. So e to the minus j 44 pi. And how much is that? Can someone tell me how much is this?
Probably is 1, is it?
Yeah, it's 1. You know, this is a multiple of 2 pi, right or not? This is same e to the minus j 2 pi. And then this how many times multiplied? 22 times, right?
Yes.
So we know our sine wave. We also know that e to the minus j 2 pi is cosine minus 2 pi plus j minus sine 2 pi. So this is cosine 2 pi plus j minus, minus j 2 pi or plus 2 pi is always 0. So we draw a sine curve and you can see it's always at the multiple of 2 pi is always 0. It's 0 here, and this sine. So this part here is 0. Then cosine 2 pi, if you sketch this, and then you'll see that cosine, this is 0 here, right? And then cosine is from here to here is 1 period. 2 pi. And then from here to here is 4 pi. So at every multiple of pi, cosine is 1. Cosine is 1. So this is 1. So that's why Zach said, yeah, it's 1. Okay, so you already calculated everything that you need to plug into this formula. And since it's lossless, this is true since this is lossless. So after getting everything, next, you plug everything in here. A 1.8. But we don't know what is VG. We know everything, but we don't know what is VG. The characteristics impedance. Z naught. Z naught is 50. One 8 VG squared. Z naught is 50. A 1 minus is what is gammas of S? Gammas of S 0 point is minus 0.0526. The rest is just plugging in numbers. Okay, so we already went through that in detail earlier. So I'm going to just go ahead and quickly finish this. Multiply everything together and then square it. Then 1 minus reflection coefficient squared. This whole thing squared. Okay, this is squared, right? So still we don't know what is VG. So we have VG is not given. How do you find VG? Any idea, anyone? So we were told that the input power is 1/8 VG squared over Z naught. Okay, we already know it's a maximum available power. So using this formula, so we know it's 3 watts maximum available power. That's VG squared. Z naught, maximum available power, do you remember? For maximum available power is under matched condition. That means the Z naught is ZG, and ZG is ZL, right? Maximum power, available power is calculated under this condition. When all this reflection at the load and the generator is 0. So for Z naught is also ZG. So I forgot to put, this is ZG. So ZG is 45, right? So just to reinforce, this is actually Z naught, but under all match condition, this is also ZG, right? So from there, you can solve for VG is the square root of 8 times 3 times ZG. Eight times 3 times 45 is equals to 32.86 volt. So once you know this, you take this and plug into that. VG is 32.86 squared. .86 squared. So if you do the number crunching, you will end up getting 2.812 watts. Although line is lossless, the power available was 3 watts, right? The power that was available, the power available was 3 watts. Idea 3 watts. And then we also we were also told that the coaxial is lossless, but the available power when it reached the load, the power that it reached the load, because of the lossless, P in, PL is P in, 2.812 watts. Cable lossless. But the available power was 3 watts. Why are we only getting 2.8 watts reaching the load? The cable was lossless. Can somebody tell me, please? BB? Bionic?
Yes, sir.
Why the available power was 3 watts, the cable was lossless, but the power that reached the load is only 2.8 watts. The 0.2 watts is lost. Where did it lose? Where was it lost? What was the loss, the root cause of the loss?
Reflection.
Okay. reflection. These are the reflections, gammas of S, and then we also have gammas of L. Okay, since this is a lossless line, the line didn't cause any reflection. Any other questions?
No, sir.
So have you guys finished the lab? Reflection. Lossless, this is the cable, right? Let's say this is a cable. The cable can be represented with a resistor. So there's going to be some losses here, ohmic losses. You know ohmic losses, I squared R. When there's a current flow, when there's a resistor, then there's a I squared R loss.
Does
Power
that
loss.
consider as heat loss, sir?
Beg your pardon?
Does that consider as heat loss? Heat loss, sir?
Yeah, heat dissipation.
Okay.
So this is nothing to do with the reflection. Dissipation, so this is lossless. There's no loss due to this. But the losses, so because there's a lossless cable, then where the loss come from? I'm asking. Yeah, the loss came from here. This is the transmission line. One line, okay. It's a transmission line, and then you have a load. The loss comes from the reflection at the load because of mismatch. And this was 50 ohms, right? What was the load impedance?
75.
This is 50, 75. So
Yes.
the mismatch here. And then there's another loss coming from here. And there's also another mismatch. Mismatch of impedances of the generator and the load. So you also going to get a reflection here. It's up to you which way you want to look. The reflection at the load, now this is a reflection at the source. We can also draw it this way. Reflection at the source or generator. If you draw this way, then the reflection, this input reflection coefficient. Let me draw this in a different color. Next time we do another example, you'll see more. Sometimes you use an attenuator to reduce the power to a measuring instrument because the measuring instrument cannot take high power. So you want to attenuate the power so it won't damage the equipment. So P in is 8 dBm. And then P out is what? I'm asking you. If you use a minus 2 dB attenuator, there's one way to calculate, the two ways to calculate. First, I'll show you a way to calculate. This is a kind of long-winded way. Okay, one way to, you know dBm, the definition of dBm. So first, you can convert dB one way. Convert dBm to milliwatt. So how do you convert P in? I want to convert P in from dBm, so dBm to milliwatts. So 10 log P in divided by 1 milliwatt is equals to 8 dBm. So log P in 1 milliwatt. If I divide by 10 on both sides, you get 10 divided by 10 on this side, it will be 1. On the left side, 10 divided by 10, 8 divided by 10 on the other side, it becomes 0.8. Therefore, P in over 1 milliwatt is equals to 10 to the power of 0.8. So this is a log base 10. So you throw the base to the other side, it becomes the base. Okay, 10 to the power of 8. And therefore, P in 10 to the power of 8, 10 to the power of 0.8, that's going to give you 6.3096 milliwatt P in. Okay, this is, I'm converting the given information in dBm to milliwatts. So next, I'm going to find out the P out. So the formula is 10 log P out over P in. Okay, this is a different formula. This is taking a ratio of 2 powers, output divided by input. And 10 log of that should give you an answer in dB, which was already given to you as minus 2 dB, right? Then from there you proceed solving them. Find out what, solve for P out. Sorry, 10 minus 2, you divide both sides by 10, we get okay. Then P out over P in is 10 to the power of minus 0.2. P out 10 to the power minus 0.2 P in. 10 to the power of minus 2. What was P in that we calculated earlier?
2.8. 12.
10 times 10 to the, okay, the minus 0. P in that we calculated earlier. Remember? This one.
6.3.
6.3096 milliwatts. This is P out. And if you calculate that out, that's going to give you P out is 3.9814 milliwatt. So this is the answer. This is a long way of doing it. If you don't believe me, you can always check. Let's check. P out over P in, 20 log of, this is power, right? So 20, 10 log of P out divided by P in. Both of them are milliwatts, so they cancel each other, and that will give you minus 2 dB. Okay, just checking, after finding out the P out, I just wanted to check if our calculation was correct. We can do a quick check. It's another easier way to do this. Okay, I only have 3% battery life. So quickly I'm going to end this. Another way, easier way. P out is 8 dBm. P out is P in minus, what was the gain? Minus 2 dB, right? Minus 2 dB. With 8 dBm minus 2 dB will give you 6 dBm. I just quickly draw so that you know P out, P in minus 2 dB. So this is a quicker way to do. One of them is dBm and one of them is dB. And of course, you know, they are both log. So you can add or subtract. If you don't believe me, you can go and try to convert P out to dBm. Okay, 10 log P in should give you 6 dBm. In this case, 10 log P out over 1 milliwatt is 6 dBm. So log over 1 milliwatt is 6 over 10. So therefore P out over P in for 1 milliwatt is 10 to the power of 6, 0.6. Therefore P out is 10 to the power of 0.6 multiplied by 1 milliwatt. That will give you same as what we got earlier for P out. What was the P out? Take the calculator and punch it out. You get around 3.981, which is same as before. So you'll see this is an easier way to do. So this is a longer way to do, and both of them gives you the same answer. See right here, same.